Hi everyone, Professor Granucci back again. Like I advertised in the video before, this video is going to show you basically how to solve pretty much all the problems. So feel free to skip through the things that you really need to see. If you see one and you're fine for the rest, that's fine. If you need like extra examples, of course, by all means watch them all. So don't feel like you have to watch them all, but I am going to do them all just to show you how I'm thinking, of course, and how to solve these out and where to go with it. So I'm just basically just going to, go ahead and solve the ones that are on the slide. So this was the inelastic example. I like this one mostly because it's more visual. Oops, let's go back here. Oops, oh boy. Come on now, let's go this. There we go. Sometimes you just force it. So this one is not one of those like word questions, which I will solve later because I think that is really helpful to do the word questions. But for this case, I like it because this is how you should do it all the time. When you draw your pictures to figure this out, you should always do a before and after. Now, this one already did the picture of the before and after. So we have a person they're running with a speed to the east, 4 meters per second, or forward. I'm just going to add that piece in because, like I said, momentum is directional, so it's very important that we include our direction here. This person has a mass of 26 kilograms. The sled has a mass of 5.9 kilograms, and the sled is at rest. There's a lot going on here. So velocity of the boy going in the x direction initial is what it means. You don't need that many indices. You can just call this 1 and 2. But that's what VSX means for sled. And VB means for the person like that. So before it is, you can see the person's running and the sled is at rest. And then after, the person jumps onto the sled. And then, of course, what we're trying to find is the final velocity. What is the velocity after this point right here? So before we even think about how to solve this out, I hope one of the things you got to ask yourself is what kind of collision is this? Is this a perfectly elastic, inelastic, or explosion? So to determine that, you really got to see what happens. So they start off together before. Oh, I'm sorry. That's not together. They start off as separate. But then, all of a sudden, they are together. So separate together means inelastic. In fact, a little cheat sheet. I didn't even think about this until just now, but cheat sheet. If they're separate and then they remain separate, that's an elastic collision. If they're separate together, then that's inelastic. And if they're together, then apart, that's explosion. So that's your kind of key. And the before really determines which is which. So if they're together before, that's different if they're separate before. And that's kind of like a little cheat sheet for you. So with that in mind, separate together, this is an inelastic collision. This information tells us what equation we're going to use. In fact, it's going to be like this. M1 V1I plus M2 V2I is equal to M1 plus M2 VF. So M1 just means the first object and M2 means the second object. It really doesn't matter which you put here. As long as whatever you put as 1 here, it's also 1 here. That's actually the most important part. So I'm going to go ahead and do it. So I'm going to call this one mass 1 and this mass 2 for no particular reason other than this is first. So 26 kilograms times 4 meters east plus the sled, which is 5.9 kilograms, times 0. Now, if you want to shortcut this and just ignore this whole term, you can, because 0 times this will just be 0. But I want to put it here to, of course, as a placeholder and show you that I am applying this equation. So M1 is 26 kilograms plus 5.9 kilograms V final. Okay, so now I'm going to go ahead and, so as you can see, it's pretty much set up, and now this is the physics, and this is the algebra now, is just going through it. A really important fact that I kind of just did without really mentioning is, notice that these are all going in the same direction, east. So east is a positive number, so I'm just going to put the positives up here, or at least right here. I mean, 0 doesn't really have a positive or negative feature of it, but I am including direction. So number one mistake on your quiz is forgetting a negative sign when you need it. For this question, you don't need it because it's going east. So I'm going to go ahead and simplify this. 26 times 4. Plus 0. 26 plus 5.9. VF. So now I'm going to solve this out. So basically I have to get rid of this first. This goes to 0, of course, so that pretty much goes out. So I'm going to divide both sides by 28. The answer is positive 3.59 meters per second. I mean, you could round this to about 3.6 meters per second, and it's going east because the answer is positive. So in other words, it tells us the direction too, which is good. And hopefully this makes sense. If you start off moving in this direction, and you jump onto the sled, just like this, you're going to continue moving east like that. Here's a cameo from my daughter. Okay. All right, we're going to pause for a minute and do the next question. Okay, I'm back. So that was how you can solve an inelastic collision. All right, so let's take a look at the next one. So this is an explosion. I'm going to go ahead and screen capture this. So in this question, we kind of already know that's an explosion, just because it literally says explosion example. But let's pretend. So the criteria for that is the fact that they both start at rest. And notice that's what the case is. This guy starts at rest, this girl starts at rest. And then they give us the values of their masses, right? So they have them here. And what they're doing is, if you notice, they're on skates and they push apart. It's really fun to do if you haven't already done something like this. So anyway, so they're going to push apart, and it looks like we know the velocity of this person, but we're finding the velocity of the other person like that. So the fact that they stay together and push apart is a signature example of a explosion. So let's go ahead and set up the mathematics here. So let's go ahead and do that. And let's go ahead and solve it. So explosion starts with 0 momentum. That's the before. And the after is the after velocities and masses of the respective two. Like that. Okay. So I'm going to go ahead and fill in the information. And again, 1 and 2 doesn't matter. Literally, I call this 1 and 2 for the sake of that. Okay, so 0 kilometers meters per second is equal to mass of the first person, which was 80 kilograms, times its final velocity. Now, that's the one we're solving for, so I don't know the first one. So I'll leave it as a variable, plus mass of the second person, which I didn't remember, 45, okay. Oops, too far. Still need the numbers here, sorry. The mass of the second person is 45 kilograms. And they are going 2.2 meters per second. and they're going east. So I'm going to leave this number as positive. As you might imagine, this number should be negative as they're going west. And mathematically, it will come out that way if we set everything up right. Okay, so we're solving for this. Now, a lot of big mistakes happen when you people set the, well, most people get this set up right, so that's the physics. So here's some algebraic mistakes. You can't actually divide by 80 first because this is attached. You actually have to subtract this whole thing first. You could do, whatever you want mathematically. I'm going to go ahead and simplify these. 45.2.2. So this becomes 80 kilograms V1F plus, I just simplified that to 90, it becomes 99. That's weird, but that's exactly what it is. Equals 0, right? Okay, so the first thing I have to do is actually subtract 99 on both sides. This is where the negative comes in. So I get negative 99 kilograms meters per second is equal to 80 kilograms times V1F. So 99 divided by 80 is 1.2. 4. We'll round. By the way, this is negative meters per second equals V1F. Okay, so I always check my answer. It's good that it's negative because the person is moving west. The arrow is pointing that way. Very good. And let's see, 1.2. So that seems about right. This person's heavier, so they're going to go slower. So that makes sense to me. So very good. Everything checks out with that. So that's how you can solve an explosion question. Okay, what else we got here? Oh, here's a long one. Okay, so I like this one because it's no longer a visual one, so we kind of have to think about it in a visual sense and then solve it all out. Okay. On a frictionless horizontal table, an air table, a puck with that mass is moving towards puck B, which is initially at rest. After the collision, puck A has this speed to the left, and that has that speed to the right. We type a collision. Which of the following quantities are conserved, what's the speed after, and what's the change. Long problem, okay? So let's go ahead and do this out. So I'm going to read it again. So I have puck A, and it's moving toward puck B, which is initially at rest. I'm going to wait. After the puck collision, puck A has a velocity of that to the left. Okay, so I'm going to assume that this is going forward. So it's moving toward puck B, which is at rest. Oh, I drew it right. This one is slightly bigger. Then afterward, that's the before. The after is puck A is moving to the left with 1.116 meters per second. And this is moving to the right. A little slower, faster actually. If I were to draw this correctly, this would be a longer arrow. And then this is 0.645 meters per second. This is why I like drawing a picture, because then it's less likely that you're going to mix up these numbers. So this mass is 252. And this one is 0.37. Okay. So they're separate to begin with, and then they're separate to end with. So far we know that this is a elastic collision because they separate. Now, if I want to give the word perfectly, the energies have to equal 0 in the end. So we'll find out. But this is an elastic collision. It's not an inelastic collision because they're not combining, and it's not explosion. So let's go ahead and solve it. I don't know. Well, I'll tell you this. Which of the following quantities, if any, are conserved? Always momentum. Well, momentum is because no friction. We should be very specific. I don't know about energy yet. I actually have to solve this question to really figure that out. So I'm looking for VA, the speed right here. So if I were to draw the mathematical model of this, it would look like this. MA, VIA, plus MB, VBI is equal to MA, VAF, plus MB, VBF. So notice instead of 1s and 2s, I did A's and B's, but it's the same kind of concept here. So this is a very long equation, so I'll start here. So the mass of this times V, don't know that, so that's the variable, plus MB, which is this mass, times its initial velocity, which is nicely 0, equals M. So the same M as before, so I gotta be careful, make sure I write down the right number. It's a weird 2, but that's a 2, because I didn't know where I was going with that. VAF. So notice that is backwards. I gotta give myself enough room. The recording, right? Times. Okay, so this is going right, so that would be positive. And there you have it. That is the physics. So if you get to this point, you got most of the credit. But here's the hard part, right, is simplifying all of this. I'm going to go ahead and do that. So what happens is this whole term gets dropped out because it's 0. So the whole left side becomes basically this. Equals. So now I'm just going to, you can do this however you want. I always do it separate, simply because I make mistakes. And I find that if I break it down instead of doing it as that one big giant equation, it's actually less likely that I'll make a mistake. Put me back up and me over here, I guess. That's if I round it. Okay, so now I'm going to combine those numbers. Okay, 0.239 minus 0.0292. 0.2098. This is kilograms, meters per second. I'm just going to double check my numbers. They look fine, but I just want to make sure I'm doing this right before I get committed to it, right? And that all my numbers look good, right? Yeah, it goes fast. Okay. All right. It's fine. All right, so now that I did that, I basically divide both sides by this number. So like I said, a lot of people would just make algebraic mistakes when they do this question out. That is actually the thing that most people do wrong. 0.2098 divided by 0.252. Okay, this looks good. I'll round again. Okay, so the final velocity is 8.33 meters per second, and I just said east. In other words, it's going, or right. I think they were talked about in terms of left and right, so that's actually the better way to write this. Is right, and I'm just going to verify. Okay, that makes sense. It's going fast, and then when it's separated, it's less than the two velocities, so that looks pretty good. And it's going east, that makes sense because it was going toward it. So if it was going west, it'd be going away from it. So I always like to check my answers too. So that looks pretty good. But now it says calculate the change in kinetic energy. So this will actually just determine if it's a perfectly elastic and not just regular elastic, right? So the change in kinetic energy is basically the final minus the initial, 1/2 the sum of the final minus the sum of the initial. So it looks like this. Oops, final. This is where I make mistakes too, is making sure that these are final velocities minus the initials. Okay, so then, I mean, it's not hard. It just takes a long time to do this. I mean, in that it's just a lot of calculations. So 1/2 the mass of the A, oops, A is 2, see? 252 times its final speed, which was 0.116. So its final speed squared. Now, it doesn't matter that it's negative because the square gets rid of it, but just being true to the question. VF final, I forgot that one, 0.645. Minus the initial one. So whatever answer you got from the top, you would put here. Well, I know the initial velocity of B is 0, so the good news is that this whole term is 0. I'm not going to go ahead and calculate it. All right, so number punching, here we go. And again, I like to do it not in all one. I'm not going to do this as all one giant equation on my calculator. I just don't trust it. So I'm going to do each part separately. Now you can do whatever you want as long as it comes out with the right answer. 0.00169.5. So I think with that, I'm just going to round to 170. This is in joules, plus I'm going to do that. Now this whole thing is going to subtract with this one. Oh, that's why. See? Times 0.833 squared. I was like, that's really high. All right, so there you go. $874. All right, keep going with my steps. Okay. So the change in kinetic energy is negative 0.76. So basically the negative means is that the final energy that the initial energy is final than the initial energy is greater than the final energy. Which means energy loss. energy lost. So even though this is elastic collision, it's not a perfectly elastic collision. So that's what it means to be perfectly elastic, is that the fact that this wasn't really zero. Now, I mean, we could argue maybe a little bit that this is close enough to zero, which is fine with me, because it is pretty close to zero. It's not a significant amount of energy lost. I mean, it's a pretty small amount of energy lost. I would say it's nearly, that's what I would say, nearly perfect. Is that a conundrum? This is a nearly perfect elastic collision. Regardless, that's how you find the kinetic energy. Okay. Same kind of thing. You could do it again here. But this is an inelastic collision. I know that because before they're separate and after they're together. So boom, solved that question. We'll figure that. Well, I know only momentum's conserved because first of all, it does say frictionless, which is a signature of no external force. So that's the quantity that is conserved, but not conserved is energy. I don't even need to solve it because I know in general inelastic collisions do not conserve energy. We'll find that in finding this question. So let's find the initial momentum of the system and what's the final velocity of the two blocks. So the initial momentum of the system would be, in fact, that. It would be m1 vi1 plus m2 vi2. Which is nice and easy in this case because it's just the block here. So m1 has a mass of 1.10 and it's going at 29 meters per second. I already forgot those numbers. 29.1 kilograms. So it's a pretty big block. Going pretty fast. This is incredibly fast. Just to do it, this one's even bigger, 21 kilograms, but it's initially at rest. So technically that would be it. But if you want to be a completionist, then this would be 29, right? 21. And 1 kilograms times 0. This becomes 31.9 kilograms meters per second as the initial momentum. Now, what's the velocity after the two blocks? Now, you don't have to start over from scratch the way I am, because technically you could just set this equal to the change, but I'm going to start over. So then the initial system looks like this. Oops, not double I. Plus m2 like this. And you just plug in your numbers. They're all going east. I didn't really talk about that, but if you notice, they're all going to be positive values here. And yes, you could shortcut by replacing this whole thing, which is what we already solved here. Sure, I'll shortcut it. It's the same thing. I'm not going to go through it again. That's the shortcut. But now what I'm going to do is do the 1.1 kilogram plus the 21 kilogram and do VF here. So this becomes, I don't need to do out the math for that. I can handle that math, I think. I need a new chair. This chair's gonna kill me. Oof. It's like a kitchen chair. It's not even like a real chair. A real work chair. Alright, I'm going to do 31.9 divided by 22.1. And my VF final will become 1.44 meters per second. It's positive, which means it's going to the right, which is what the image is showing. I am going to absolutely ask you that question. I'm going to ask you, is it going to the right? Is it going to the left, or is it 0? You have to put a checkbox. So in this case, it would be right. Because I want you to explicitly tell me that you know which direction it's going in, because momentum is a vector and it needs a direction. Okay, now we're going to do the change in kinetic energy. Okay, so if we do the change in kinetic energy, it looks like this for inelastic equation. The final, so we do the same setup, final minus initial. But the final looks like this because the masses are combined minus the initials, which would be squared. Ooh. Where thankfully, again, this is 0. Is that always the case? No. Is it usually the case? Yeah, which is nice. Okay, so I'm going to go ahead and put my numbers in. Mass 1 was 1.1 kilogram plus 21 kilograms times my answer from part 1 here minus and what was its initial? It was like 29, right? Its initial was 29. Yeah, it's going real fast. Yeah, this is going to see a large energy loss, I could tell, because this number is just humongous and it's squared versus that tiny number, right? All right, like I said, rinse and repeat. So I'm going to go ahead and do this. Oops. Times 0.5 has 1.44 squared. 22.91 joules minus, whew, that's a big number. Yeah, so as you can see, we're going to lose energy. And there you have it. So this is a huge loss, which is expected. And inelastic collisions. So there you have it. So as expected, there's way more initial energy than there was final energy, designated by the negative sign. Now, usually you lose energy. If you have a positive energy, I would check your math, because usually you don't gain energy unless you're being pushed, which usually is not the case. So usually it's negative or 0 or close to 0. If it's supposed to be 0 and it's close enough, you can say what I said, which was nearly, what was it? Nearly perfect. You could say something like that. All right, now we're going to go ahead and keep solving questions. Like I said, if you're done within the first 2, then you don't need to keep watching, but it's just nice to have a bunch of them, right? Suppose you joined NASA and enjoying your first spacewalk. You're outside the shuttle when your fellow astronaut, approximately equal in mass, is moving toward you with 2 meters per second. If she collides with you and holds on, then how fast did the 2 of you move after the collision? So you're probably like, oh no, there's no mass. Well, good news. Usually the masses can cancel. So first are like this. So we have m. Since these are all the same masses, so we'll call them m. So m times 2 plus the momentum of 0 is equal to the sum of the 2 of them times what we're solving for, right? So we get 2m, notice what I did there, is equal to 2mv. M's cancel, so I get 2 equals 2v. If I divide 2 by both sides, I get 1 equals v's, meters per second. And of course this is positive, so we're moving right. So yeah, if you don't have a variable, it's most likely that it's going to cancel out like it did here. Remember, anytime you have a symbol on each side, just like energy conservation is independent of mass, you could have this. But this is a special case, so it's not always independent of mass. They just happen to be the same mass. So that's moving with essentially half the speed because they're gaining weight when they do that. So they're moving slower because they are heavier. So hopefully that makes sense. Part 2. So now you're outside by yourself and you have that mass and you're doing some work with your wrench, but somehow you drifted away. So, you know, in physics class, that momentum must be conserved. So if you throw your wrench away, that should bring you back to your ship. So let's see. Suppose you throw the wrench at that speed. What is your resulting speed? And if your ship is that far away, how long does it take? Okay. This is an explosion. I hope you noticed that because you start off together and go separate. So I have 0 is equal to m1 vf1 plus m2 v2f as such. So it will look like this. M1 is 65 kilograms. Now I throw this wrench at 13 meters per second to the right. And then the size of the wrench was 2, right? Yeah, the mass of the wrench is 2. And we're looking for VF. So if I solve for this, I get 0 is equal to 845 kilograms meters per second plus 2 VF. 2, I mean, you know what I mean, the other guy. But now I have to move this over, so I actually have to subtract both sides by 845. So I get negative, which is good because we should be moving opposite the way we threw it. And then we divide both sides by 2. Yeah, I think I messed this up. Hold on, because this looks ridiculous. Yeah, sorry about that. I'm not going at that speed. It's the wrench. I was like, man, that's really fast. So let me fix this mistake. You might have noticed it before too. I was like, man, this is coming out wrong. It's okay. I'm human. I make mistakes. I'm glad that I caught it. That's the most important part. So 65 is what we're solving for. The wrench is going 13. So my fault. Sorry about that. I knew that looked really weird. So we're looking for this. The initial person. And actually, since I'm modeling it, the wrench is actually going west. So this is negative. So here we go. That looks a lot better. Oh, man. Man, that does not look right. So that should be negative 26 kilograms meters per second. I have to add this to the other side, which is good because it should be moving forward. So 26 kilograms meters per second is equal to 65 kilograms V1F. I have to divide both sides by 65. My son is screaming so loud in the other room. Okay, so I get 0.4 meters per second. So, you know, not fast, but doable. So how long? So if you are here, actually, we want to put us over here. This is, and then the space shuttle, right? So the space shuttle is like, I don't know what you put on this thing, stripes or something. I don't know. That's good enough. Okay, so we're 150 meters away. So we're pretty far, right? And now that we threw that wrench, we're moving in this direction, which is good, with this speed. So how long does it take? Well, if we're moving at a constant speed, then we could find our velocity as delta x over t. So 0.4 meters per second is equal to how far we went over t. T is going to be 150 meters divided by this. Remember the flippy. As long as they're in this order, you can switch them. So 375 seconds, which is the answer, but I'm just curious, which becomes 6.5 minutes. So it's a long time to get back, but at least you're getting back, right? You don't want to be stuck out there. So that's how you can figure out how long it takes to get back. Like that. That's a very, this is a very, what should I say, not cliche, but is a standard problem in physics, is this wrench one. Okay, perfect. One more. An ice skater at rest, an ice skater at rest catches a bag of sand moving north. So I'm going to call north this way. Here's the sand. And this is going 5.4 meters per second. And this person's at rest with ice skates on. And then it causes both ice skater and the holding the sand now. They're both together, moving at 1.5 meters per second. I don't know. Ice skates, there we go. Like that. And the question is, what is the mass of the sand? All right, fun. Now I hope you know we started separate and came together, which means inelastic. Elastic equation, I just got lazy and didn't write the whole thing. So m1 v1i plus m2 v2i is equal to m1 plus m2 over vf. Okay, but we don't know the mass of the bag of the sand, so m1 times its velocity, 5.4 meters per second, plus the mass of the person, 63, times its velocity initial, nicely 0, is equal to m1 plus m2, which is 63. So we still don't know that, so that's fun. But we do know the final velocity is north, 1.5 meters per second, which I will just verify. Yes, that's correct. How do we solve this? Well, first of all, this is going to be 0. Very nice. I'm going to do 5.4 and put the m here is equal to. So what I'm actually going to do is distribute this. So then I get 1.5 m1 plus the multiplication of those. This allows me to isolate m1, 61, 94.5. I got lazy with units here, but you can see what I'm doing mathematically. Doing this allows us to separate m1. I can't just subtract out 63 here because it's attached to this. And I mean, I can divide this by 1.5. You can actually do that. That's another method, which I didn't think about, which would have been easier, but that's okay. It's just another tactic for you to do this. So what I'm going to do is subtract m1 here and carry it. So 5.4 minus 1.5 gives me 3.9 m1 equals 94.5 kilograms meters per second. In which case now I divide by the 3.9. on both sides. M1 perfect. That's the answer. It's always nice. 2-3 kilograms. It's a heavy bag of sand. Sand is heavy. And that looks about right. So it's not bigger than a person, good, but it's pretty heavy, which makes sense. So that's our last type of problem we can see when, solving this. So in other words, this problem I like because, first of all, it's not solving a velocity, it's solved for a mass, but we had two missing variables of mass. So that's how you can kind of treat that type of example when solving this. So in summary, like I said, I'm not going to solve these, although they're very interesting questions. But just in summary, I kind of liked what I said before. Here is what you need to know. If they're separate before and separate after, that's perfectly elastic collision. If we start off as separate but come together, that's an inelastic collision. And if you start together and you are separate or apart, that's an explosion. These are three types of collisions. They all have their own, oh no, I didn't mean to load my gallery here. Stop. They all have their own equations, which are in our slides. And once you know which type of collision you have, you can apply the correct conservation of momentum equation. But just know that this is actually always derived from conservation of momentum. It's not that there are three different equations. But like physics in general, we can kind of categorize them into the three types. But what we're doing is we're modeling what's going on with those equations. That if you have something together, you have to add them up. Just another note, together, but at rest. I really should actually stress that. This is an explosion, because you could be moving and then separate, which is the inverse of this. So notice that explosions do have to be at rest when we do that. If you have any questions regarding how I solve anything, please feel free to send me emails. I'd be happy to answer them. In addition to that, if you have any questions about my math, feel free. If you did your math differently, it's okay as long as you get the same answer. Of course, you can't make up your math. But if you did something different or you saw something faster than I did and did it your own way, it's totally fine. It's not about the, it's a lot about the way, but you know what I'm saying. There's different methods to solve questions. Okay, this concludes our video on solving conservation momentum mathematical problems.